A single mistake, and this machine can come to a complete stop. Not because the engine failed. Not because it ran out of fuel. But because of a tire. And not just any tire, a tire taller than a two-story building, carrying more weight than 50 cars combined. Now here's what makes it even more intense. That tire is holding up a machine weighing nearly 600 metric tons, moving across sharp rocks, extreme heat, and constant stress. So how does it not collapse? And what really happens when it suddenly explodes? Before we talk about the tire, let's understand the machine it's attached to. The Caterpillar 797F. The world's largest mechanical drive mining truck. It stands 6.5 meters tall. It stretches over 15 meters long. Its gross weight when fully loaded reaches over 623 metric tons, the equivalent of more than 400 standard cars stacked on top of each other. Its top speed, even when loaded, is around 68 kilometers per hour. That's a 6-story building, moving faster than city traffic. And the only thing connecting this machine to the ground? 6 tires. Each one measuring up to 4 meters tall. Each one weighing between 2,000 to 5,000 kilograms. These are called OTR tires, off the road. And they are unlike anything else on the planet. So how do they actually handle this kind of extreme load? The answer starts with something surprisingly simple: distribution. These trucks are carefully balanced. The weight of the load is spread across multiple axles, and each tire is engineered to carry a specific share. Even then, each individual tire supports more than 100 tons on its own. That's not something ordinary rubber can handle. Which is why these tires are built completely differently from anything you've ever seen. Inside every giant mining tire is a hidden structure made of high-tensile steel cords. Think of it like a flexible skeleton. This structure, known as an all-steel radial design, allows the tire to flex under pressure without tearing apart. It gives strength, but also controlled flexibility. Because a tire that is too rigid would crack under the constant punishment of a mine site. The standard tire on a Cat 797F carries a designation 59/80 or 63. Numbers that represent its width, aspect ratio, and rim diameter. These aren't bought at a shop. They are engineered to order. Manufactured by companies like Michelin and Bridgestone. In fact, just to transport 6 of these tires before assembly requires 2 separate semi-trailer loads. But even with steel reinforcement, the real hero here is something you can't see at all. Air. These tires are inflated to extremely high pressures, creating a powerful internal force that supports the entire weight of the truck. The compressed air distributes the load evenly across the tire's surface, preventing weak points from forming. But this balance is delicate. If the pressure drops too low, the tire begins to deform. The sidewalls flex too much. Heat builds up from the inside. And the damage becomes invisible until it's too late. If the pressure is too high, the tire becomes dangerously rigid. Brittle. Increasingly vulnerable to sudden rupture. So every tire is carefully calibrated based on load, speed, and terrain. Because in mining, conditions are never constant. And that brings us to the next challenge: heat. When a mining truck moves, its tires are constantly flexing under enormous load. And that flexing generates heat. Enormous internal heat. Heat is the silent killer. Too much of it weakens the steel cords inside, degrades the rubber compound, and causes failure from within, completely invisible from the outside. This is why engineers use a critical metric called TKPH. Ton-kilometers per hour. It's a formula that calculates the average load on a tire multiplied by the average speed of the truck. It measures how much thermal stress a tire is being asked to absorb. Knowing your site's TKPH requirements plays a vital role in selecting the correct rubber compound, because the wrong compound in the wrong mine will fail far sooner than it should. But even with all of this engineering, tires can still fail. And when they do, the results are dramatic. A tire blowout on a 600-ton mining truck is nothing like a flat tire on your car. It's violent. Sometimes explosive. Inside the tire is a massive volume of compressed air. When the structure fails, that air is released instantly, creating a powerful blast wave. Safety exclusion zones must be maintained anytime a tire is being inflated or inspected, because the consequences of failure at that moment can be catastrophic. So how are these failures caught before they happen? Modern mining operations use real-time tire pressure monitoring systems. TPMS. Sensors embedded in each tire transmit live data to the operator's cab and to remote fleet managers, tracking pressure and temperature continuously. The moment pressure drops, or temperature climbs past a critical threshold, an alarm fires immediately. These systems are engineered to withstand the extreme heat, vibration, and abrasion found inside a working mining tire. Because a sensor that fails in the field is useless. This technology alone has saved mines millions of dollars, and more importantly, it has saved lives. But if a blowout does happen, despite everything, the priority becomes control. Despite their size, these trucks are designed to remain stable even when a tire fails. The suspension system absorbs the sudden impact. The remaining tires redistribute the load as quickly as possible. The driver trained for exactly this scenario slows down gradually. Not sudden braking. Not panic. Replacing a mining truck tire is not a job for 2 men and a jack. It is a full industrial operation. The truck must first be lifted using massive hydraulic equipment capable of handling hundreds of tons. Then the tire itself, weighing several thousand kilograms, is removed using specialized tire handlers. Human strength isn't a factor here. Everything is mechanical. Because a single mining tire is not just expensive, it is extraordinarily expensive. Prices range from $10,000 for smaller models to over $40,000 for the largest tires fitted to ultra-class haul trucks. To squeeze every possible hour out of a tire, mines rely on several strategies. Road management. Haul roads are kept as straight and smooth as possible because for every 1% change in grade, the load shifts 2% across the tire's contact patch. Curves, ruts, and sharp debris all accelerate wear. Driver training. Smoother driving inputs, consistent speeds, and careful cornering can dramatically extend tire life. In this world, a tire is not just a component. It is the foundation of an entire operation. Every ton of copper, iron ore, or coal that reaches the surface does so because 6 tires, inflated with precision, reinforced with steel, and monitored in real time, held together under impossible conditions. The next time you see a bridge being built, a phone being manufactured, or a car rolling off a production line, somewhere at the beginning of that chain was a machine moving through a mine, held up by a tire.